Have you ever looked up at a wind turbine and wondered, why does it have three blades? Not two, not four, not six, always three. It seems like such a specific choice. And here's the thing, if you add a fourth blade, you actually capture more wind energy. So why don't wind turbine designers just do that? Why stop at three? The answer might surprise you. It turns out that building a better wind turbine isn't just about capturing as much energy as possible. It's about finding the perfect balance between physics, engineering, and economics. Today, we're uncovering the truth behind one of the most overlooked design decisions in modern energy. Let's dive in right here on Simple Things of Time. Wind turbines are one of the fastest growing sources of clean energy on the planet. In 2023 alone, wind power generated enough electricity to power hundreds of millions of homes worldwide. They're elegant, they're massive, and they're everywhere. But despite how common they are, most people have never stopped to question one very basic thing about them: the number of blades. At first glance, more blades seems like the obvious answer for more power. After all, more blades means more surface area to catch the wind, right? And if you look at old-fashioned farm windmills, the kind used to pump water, you'll see they often have many blades, sometimes a dozen or more. So why did the wind energy industry land on three? To understand the answer, we need to talk about how wind turbines actually work. A turbine doesn't just catch wind like a sail. It works more like an airplane wing. Each blade is shaped so that air moves faster over one side than the other. That difference in airspeed creates a pressure difference, which generates lift, the same force that keeps a plane in the air. In a turbine, that lift is what spins the blades around. The spinning blades drive a generator, and that generator produces electricity. Now here's the key detail. There's a limit to how much energy any turbine can extract from the wind. It's called the Betz limit, named after the German physicist Albert Betz, who figured it out in 1919. No matter what you do, no matter how many blades you add or how clever your design is, you can never capture more than about 59% of the wind's energy. The air has to keep moving after passing through the turbine, otherwise it would just pile up and stop flowing altogether. So the race isn't about capturing every last bit of wind. It's about getting close to that limit as efficiently and as cheaply as possible. And that's where the number of blades becomes a fascinating puzzle. Let's start with one blade. Yes, one-bladed turbines exist, and they actually spin very fast and can be fairly efficient. But they're incredibly hard to balance. Imagine a ceiling fan with only one blade. It would shake itself apart. Engineers have to add a counterweight on the opposite side just to keep the turbine stable, which adds cost and complexity without adding any power. Two blades are much better. They're balanced, they're simpler, and they work reasonably well. In fact, the early pioneers of modern wind energy experimented heavily with two-bladed designs. But two-bladed turbines have a problem called the teeter effect. Because the two blades are always on opposite sides, when one blade passes in front of the tower, the whole rotor tilts slightly. That wobble creates stress on the structure and makes for a bumpier, noisier ride. You can manage it with engineering tricks, but it adds complications. Three blades solve both problems beautifully. With three evenly spaced blades, the turbine is naturally balanced in all directions at all times. No wobble, no teeter, no need for counterweights. The rotation is smooth and steady, which dramatically reduces wear and tear on the structure and means the turbine can last for decades. Now, let's look at some real-world numbers. A typical modern three-bladed turbine captures around 45% of the wind's energy, very close to that theoretical maximum of 59%. Adding a fourth blade only pushes that number up by a tiny fraction. In some tests, going from 3 blades to 4 only improved efficiency by about 1 to 3%. That might sound fine until you realize what a fourth blade actually costs. A single turbine blade on a large offshore wind turbine can be over 100 meters long, longer than a football field, and cost upwards of $300,000 to manufacture and install. Adding a fourth blade means more material, more weight, more structural stress on the hub and tower, more complex engineering, and more maintenance over the turbine's lifetime. All of that cost for a gain of 1 to 3% more electricity. The math simply doesn't work out. There's also a physics problem with 4 blades. As you add more blades, each new blade starts to operate in the disturbed air, called the wake, left behind by the blade in front of it. With 3 blades, there's enough spacing for each blade to hit relatively clean, undisturbed air. A fourth blade cuts into that clean air gap and ends up fighting against the turbulence created by the other blades. You add a blade, but you don't actually get a full blade's worth of extra power. And the heavier rotor from 4 blades creates another problem. It's harder to control. When wind speeds suddenly change, a gust hits or the wind drops, the turbine needs to adjust quickly by pitching its blades at a different angle. With 4 heavy blades, that response is slower, meaning the turbine either misses energy during gusts or risks getting damaged in extreme winds. So why does the instinct to add more blades persist? Partly it's the same logic as old farm windmills. Those many-bladed designs made sense for pumping water because they needed high torque, a strong turning force at low wind speeds. They didn't need to spin fast. Modern electricity-generating turbines work the other way. They need to spin fast and efficiently, which actually favors fewer, longer blades. There's also a visual element. Something with more blades looks busier, more active, more powerful. A turbine with 3 long, sweeping blades spinning slowly can look almost lazy from a distance. But looks are deceiving. Those blades are moving at enormous speeds. The tip of a blade on a large turbine can travel at over 300 kilometers per hour, even when the rotor itself is only making about 10 to 20 full rotations per minute. There's something elegant about this truth. The fact that 3 blades turned out to be the optimal answer isn't just a happy accident. It's the result of decades of testing, research, and real-world experience. Engineers tried 1 blade and 2 blades. They experimented with 4 and 5. And they kept coming back to 3, not because it was the most obvious choice, but because it hit the perfect intersection of efficiency, durability, cost, and physics. Nature works the same way. A triangle is the strongest geometric shape. Many structures in nature, from snowflakes to the arrangement of seeds in a sunflower, repeat patterns that optimize for balance and efficiency. Wind turbines, it turns out, follow the same principle. 3 is the number where everything comes together. So the next time you see a wind turbine on the horizon, you can appreciate what you're really looking at. Not just a simple machine catching the breeze, but a carefully engineered solution to a complex problem, one where adding more would actually give you less. The 3-blade design is a reminder that in engineering and in nature, the best answer isn't always the biggest or the most obvious one. Sometimes the best answer is the one that finds exactly the right balance. The myth that more blades means more power may feel logical, but the reality is far more interesting. It's a reminder that questioning what seems obvious can lead to some of the most fascinating discoveries in science and engineering. If you enjoyed this video, don't forget to like, subscribe, and stay tuned for more stories about our fascinating world. Alright, that's all for now. Thank you for watching.